Hello, this is Nitin Dahad with the Times. I'm talking today to Ron Kelly, who's the president and CEO of a company called Ambature. Ron, hello.
Hello, thank you for your time.
How are you doing?
I'm very well, thank you. How are you?
And we're here in the UAE, and you've just been doing a little bit of a Middle East tour.
Yes.
But you've just sort of, before we go into a little bit of the company, just tell us there's a bit of news from this week.
Oh yeah, no, recently, as 10 days ago, we actually had a significant milestone in the roadmap for the company. We signed one of the large companies in Silicon Valley that had particular expertise in what we needed to go from lab to fab, which is a classic term under the CHIPS Act and how you develop your company's technology, particularly in the chip area. And we were very happy to say we signed just before a conference that we presented at last week in Saudi Arabia. And it's a very important milestone in the company. So very quickly, we hope, within the next year, we'll be able to tell people that we actually have been able to transfer the technology from the lab to a fab, a typical recipe or PDK, if you will, in chip parlance, and we'll be able to scale our technology.
And what detail can you, without telling, I don't think you can name the company yet, but what is it that the news is about? What have you signed?
Well, what we've signed is a joint development agreement with a typical statement of work where each of us agrees what we're going to do, what they're going to do. It's always a collaborative effort at this point in a typical chip roadmap, and we're very excited about it, obviously. The old goal is to be able to promote our quantum sensor SQUID at scale in commercial quantities for our military and our commercial markets.
Which is a good segue into tell me a bit about your company.
So Ambature is very focused in the area of quantum sensors, quantum processors, and how they all relate to artificial intelligence.
Yeah.
We bring the data that's generated from our quantum sensor, use our quantum processor to process the data, and combine it all at the edge for AI, or in a data center, as the case may be. The company's been around about 12 years. I've been the CEO for about 10 and a half years. And we are very, very focused, as I say, in getting to commercial quantities for the quantum sensor initially, which is our big focus. It was much easier to do a quantum sensor, which is called a SQUID, Superconductor Quantum Interference Device. Before you actually make that leap to the processor, we technically make something called a Josephson junction and a SQUID, Superconductive Quantum Interference Device. People may recognize this. These are some of the core architectures for actual superconductive qubits. So if people are familiar with that, we actually aren't doing qubits at this point. We use it for high performance computing and high performance sensing.
And this is a very direct question, but why should anybody care about what you're doing?
Well, they could care because we have actually taken some of the core challenges you have in typical CMOS semiconductor technology, and we've actually taken it to the next level by superimposing and growing quantum technology on silicon. And it is just a function of time. People worry about Moore's law running out and all this kind of stuff. What we've done is we've actually figured out how to make things like chiplets, how to actually grow on silicon where you can take advantage of both. Particularly important as to how you want to go to market, because you want to be able to develop a technology, typical PDK that works in typical 80-inch foundry, for example. And that's why this recent commercialization contract is so important to us.
And I guess there's benefits, and I think I'll talk to your board member Raj Jammy in a few minutes. But there are benefits to what you're doing.
Yeah, well, it is a truism to say that quantum sensing, depending on what your use case is a significant step up from traditional kinds of sensings. And what we've done is we've taken it to that level. It is actually this device that can be an excellent military use case device. It can actually be a commercial use case device, over 100 use cases in terms of what we're trying to do, but it is a significant leapfrog above traditional sensors.
Okay, well, let's talk to Raj now a little bit about the technology. So to talk to about some of the technology, we're going to talk to Raj Jammy, who's a board member at Ambature. Raj has got a background from IMEC, from IBM, and so he brings a lot of the technology expertise to the company. Raj, hello.
Hello, Nathan. How are you?
I'm fine, thank you. So we're just talking to Ron about the business. Tell us what's so good about the technology. Why were you brought onto the board? Why did you get excited?
Well, I'm easily excitable, I guess, but keeping that to the side, superconductors are something that I have worked with from my graduate studies days, and so I have an innate interest in them, and also a little bit of an understanding, I hope, in how superconductors can transform many of the technologies that we are working with today. Not only do they conduct electricity at zero losses, but they also give us the opportunity to change devices from what we use today to some new paradigms. And that helps us in improving computation density. It helps us in making sensors that are
computational density, I think, is key. Yeah,
Computational density is absolutely critical, but it also it has the potential to reduce the energy consumption problem that we all face. The power wall that we are talking about, to some extent, how do we handle all the data that we are creating and the data wall that we are hitting, and the consequent energy losses, plus some really super sensitive sensors that are quantum sensors that can transform the way we sense certain things today.
So I think in your previous company, I've attended many ITFs in the recent years where I make ITFs where they talk about the power wall, the memory wall.
Absolutely.
And I think people like Luke and Subhashish Mitra have talked about that. I mean, give our viewers, readers, a sense of where superconductors can really make a difference there in terms of some metrics.
Right. I mean, from a metrics perspective, let's just talk about the fact that 60% of the energy today in chips is consumed by data motion or data movement, right? From logic to memory and so on. So industry is looking at a number of ways to minimize that. One, of course, is to say, I am going to do something radical, switch to photons. But
there's a lot of talk about silicon photonics.
There's a lot of talk about silicon photonics, and perhaps that's going to come through. But the problem with that is you still have to produce those photons. So that's an energetic process. And then you have to detect those photons. That's also energetic. And you need some interaction between the photons and electrons to actually get the desired effects. Second part of it is people say, oh, I'm going to take my processing, or I'm going to take my data to the memory and get some processing done there. But that's still energy intensive processes at the end, right? That helps us quite a bit. From where we are today, it's an improvement. But in the longer run, I think what we really need is a way to minimize that energy to a point where we have significant advantage in doing all the computing that we need to do, given how much of computation we do today, but minimizing the energy footprint. We simply can't produce the energy that is necessary by 2040, 2050 timeframe. And many projections actually say that by 2040 we are going to exceed the world's energy production just for computing.
I've heard that from Mark Papermaster at AMD in several keynotes over the last few years. And I know you've worked with him on some of the CHIPS Act stuff, so I guess that data is solid.
The data has been looked at by several people, and Mark does a phenomenal job in explaining that to everyone. But I'm sure even Luke has talked to you about that, and a lot of people have actually faced that problem, or have come to face the problem. We all realize it in the industry that we need to do something to reduce the energy footprint of computation very quickly and very rapidly.
So let's come back to where you are with Ambature. So you've proven a technology, the quantum sensors, the squid. Where are you going next? I mean, you've also done some, because to put it onto silicon, how does it get manufactured? I think.
Right. So there are several key things happening, right? At Ambature, what we've done is we have been able to prove a unique way of growing the films, which gives a significant advantage with coherence length, and that is a first step. And I mean, keep in mind that the materials that we work with have the potential to superconduct at higher temperatures than liquid helium temperatures that the industry uses today. So that makes it quite attractive, and it's easily deployable.
So you don't have to go down to -273.
You don't have to go to, exactly.
Whatever it is.
Exactly. So liquid nitrogen temperatures would be good, but of course we can cool it down further so you have it in deep superconducting state. So existing infrastructure for current superconductors is still good. You can use this at that point too. But it has the potential and advantage to minimize that problem. So that's one aspect of what we do. In terms of where we are right now, we are taking that material. We have been able to demonstrate that we can put it on silicon with the right buffer layers and get the right epitaxy. Second step now is we are trying to form Josephson junctions with that material. And that's where some of the things that Ron might have mentioned to you earlier with regards to working with commercial players, so that you can take these technologies from the lab, where we have done it in universities, to more commercially scalable, industry-friendly, fab-friendly tools is underway right now.
And one of the things is, because you're getting the computational density, you don't need to go down to like the 5 nanometers, 2 nanometers.
Correct.
You can do it at 28 and 40, I guess.
Right. I mean, you're in some sense you are able to reset the race to the bottom, if you will. You're able to now start doing these computations at much larger nodes, but you still have the ability to process information faster and better and also cooler. So that's a big advantage too.
So in terms of manufacturing, it's on a, you're taking it, trying to sort of adapt that to existing processes, and that's what you'll then deliver as IP to your customers, who will then develop that with their customers. Is that right?
That's correct. I mean, our idea is that the core technology of how the material is put down and how you process the material to either make junctions, or how do you make interconnect with the material, or any sensors, quantum sensors with the material. So this is the core IP that we bring to the table, and the variety of applications that can be unleashed is something that different customers can do. So we could be taking some of those verticals and then working on those applications, but I believe, and the company believes, that it is going to be far more effective and far more powerful to let others who have better knowledge of the market space that they're dealing with to start doing that.
And I think one of the other areas we talked about is people get, I think, stuck on, or maybe media get stuck on, oh, this is the next big thing. But it's important to understand this is part of a whole ecosystem and value chain and solution, and it's not the be all and end all. You have to,
Correct.
it's a kind of a heterogeneous architecture.
Absolutely.
And you're building like opportunity, but giving customers the potential to build it as a chiplet into something, or
Right.
or build different architectures to get different aspects of the computation done. Is that right?
No, you hit the nail there, and thank you for bringing that up, because in any technology, even when we brought silicon technology with chips, yes, we adapted that and adopted that much faster than any other technology on the planet ever before.
Yeah.
But what we have come to now is that all future improvements that we make, each one of them may be a mini revolution by itself from a technological point of view, but all these mini revolutions will have to come together in an evolutionary manner based on the need from the systems and based on how the ecosystem develops, whether you have the right design capabilities, whether you have the right tool sets and the materials and processing capabilities. The whole ecosystem has to come together. But future of computation is heterogeneous. And this is very likely going to be one of the heterogeneous components that will impact what we are going to use in future. For example, even quantum computing requires superconducting devices, or at least one of the options is a superconducting device, and so we are excited about that as well.
But you said, I mean, with quantum computing even, you have to feed in the data.
Absolutely.
Because at the end of the day, the quantum computing is not going to be like a PC, but it's going to be doing the number crunching. Is that right?
Well, it would be like using a bazooka to kill a fly if we were to use quantum computers to do what we do today in our computation, because quantum computers are naturally geared towards doing some things that are humanly not possible today. And that's where companies like IBM and Google and others are focused, and they're doing a phenomenal job in that direction. But what would be very important for us is, as we deal with what is humanly possible for us and humanly interpretable, we do need to parse the data. We do need to feed the data appropriately for our consumption as well as for such machines, high performance quantum computing machines. So that's why you might have heard the term hybrid computing. People are calling it hybrid computing because you have a mix of both.
Yeah. From a technology point of view, what's your biggest challenge when Ambature talks to its customers? What are they not understanding?
No, it's not a question of not understanding. I think the customers who are in the field and who have these needs instantly get it. They know this. And we have often, Ron and I and others, we've often talked to our customers, and they say, we want it yesterday. Can we please accelerate this?
I hear that a lot from every company I interview.
Exactly. So they want it yesterday. On the other hand, when we talk about potential applications in future, there are some applications that are relatively near term, and then there are some that are really strategic but farther out. There is a certain degree of healthy skepticism because, can you really do that, or can it really happen? But that's exactly what 5 years ago when people said, can a car drive by itself? When COVID struck us, do we have a vaccine for it? mRNA, is it going to work? So there's always a healthy skepticism for all new technologies, and I think that's normal. That's the phase we see.
Well, thanks, Raj. So we've heard from Raj about some of the technology, advantages of your quantum sensing technology, and what are you doing in terms of go to market? What are your opportunities right now?
Well, the immediate significant opportunity is actually military use cases.
Okay.
We spent the last couple of years developing our go-to-market strategy in the military vertical. It's no big secret that there's a number of challenges around the world in terms of conflicts, and we happen to be in the right place at the right time for that. We spent a lot of time working with defense primes, with the US military, the Canadian military, potentially here the Middle East militaries, in order to make sure that we fundamentally understand what the customer needs and what the value proposition needs to be effective and penetrate those markets. Our preference is actually not to make and sell. We prefer to design and protect our designs with intellectual property and filing patents, etc. And that seems to be very successful for us, at least to date. So we hope that this formula will work. But we really would like to just rely on defense primes and commercial primes, for example, to bring our product to market.
And there's two different benefits. I mean, for the military and for commercial, there's different ways in which this really benefits these customers. Just give us a little bit of a highlight.
Well, the functionality is the same.
Obviously.
We are a classic dual-use opportunity, but if you're making something for the military, we like to say it's to military spec. They have very specific kinds of functionality that they need to integrate into various, weapons, etc., or signal intelligence programs, or identifying threats from farther distances with greater accuracy, for example. The Squid is an exquisite sensor for those kinds of functions. But for every one of them, there is a commercial use case. For example, if you're trying to develop a sensor for the military, what that becomes in the commercial world is a very, very good commercial cell phone base station filter, for example.
Okay.
It solves the Q factor problem, it solves the bandwidth problem, which you then in turn use to add to the Justice Injunction processor, which is one of the panaceas we hope for eliminating the inefficiencies in data centers.
Okay, and that then leads to potentially a significant reduction in the power requirements of the data, although you've got some trade-offs.
Yes, we are superconductors at our heart, so we have to cool our technologies and our devices to put them in a superconductive state and also keep them in a superconductive state. But for example, you're now spending 40% of your typical OPEX in a data center just on cooling it because it's generating so much heat. The beauty of superconductors, after you put them in a superconductive state, is the electrons move through the server racks with no resistance. The typical RC is what we call it in the semiconductor parlance. So we solve that problem because superconductors don't generate any heat. So we have the offset of cooling to put our technology in a superconductive state versus the offset of cooling of what it costs to cool an entire data center.
Okay. Now you came to this company, you were attracted by the IP, you're an IP lawyer, I think. What was the attraction? What did you think was really cool about this?
Well, we actually have one of the largest high-temperature superconductor IP portfolios in the world. I have a background in IP and specifically things like medical imaging. The immediate interest to me was how you could actually take their technology and the number of use cases that we had just to change healthcare. Healthcare, people don't realize, is an enormous market around the world. There is room for significant improvement at multiple levels. I have a particular background in a number of medical diagnostic technologies. So what I saw immediately was an opportunity to change healthcare by making smaller diagnostic devices so they can be deployed at the point of care in doctors' offices, and then bring AI at the point of care so you can have a better diagnosis and you can have a faster diagnosis, so little things like even medication scripts can be granted in the doctor's office rather than send someone to a hospital for medical imaging, send someone to an imaging center for a medical image. This takes 2 or 3 days and it just clogs up the entire workflow.
And now at the stage you're at, you're looking for, I mean, you've been sort of getting good investment from existing like individual shareholders.
Yes.
But now I think you're looking for the big dollars. And so that's why you're here in the Middle East, but also looking elsewhere.
Yes.
Significant funding, but what's that funding going to enable you to do?
So it will enable us to scale significantly in terms of people, developing markets, development people, salespeople, being able to have better physical facilities. We have traditionally used university labs, for example, which are amazing. University of Waterloo, for example. But we're at the point now, or the tipping point, where we would love to have larger facilities, more people developing regions like the Middle East. So this is what the use of proceeds would be.
Okay. Well, Ron, thank you very much.
You're most welcome. Thank you for your time.